This is a $3,000 real gas turbine turboprop engine, and today we're going to try something that's never been done, direct driving an RC car. But before we try to cram this beast into an RC car, we need to talk about why it's so special. A typical gas turbine, whether RC or full-size, operates on a very simple principle. It draws air in here in the front, squishes it down here in the middle, adds fuel and ignites it, and then pushes those hot gases really fast out the back. And because of Newton's third law of motion, all that gas being pushed out the back pushes the turbine forward and whatever's connected to it. However, this thing's different, and it's what makes me really excited for this video. Instead of the engine ending here in a nozzle like most gas turbines, this thing's got all this stuff hanging off the back, or the front in this case. And instead of the hot exhaust gases exiting out the back and pushing the turbine forward, it drives this. This is a turboprop or turbo shaft gearbox, and essentially it's connected to an additional fan right here that's driven by the hot exhaust gases. As we're gonna see in a minute, those gases come out of these pipes on both sides, the shaft runs through the middle, and then the very high speed of that fan, or turbine as it's called, gets reduced in this gearbox while the power gets increased. Our goal is to put a gear or something on this output and use it to actually drive an RC car. However, before we do that, we need to make sure this beautiful piece of mechanical jewelry actually works. To find out that, we're gonna need a test stand, and I wanna make the stand as exotic as this engine is. Of course, we could make it out of wood or aluminum, but that's kind of boring. Instead, we're gonna try to 3D print it out of this crazy PPS carbon fiber by Bamboo Lab. I've never used this before, and I don't think anybody's ever made a 3D printed mount for a gas turbine, but between this and some gold, I think we can do it. This turboprop mounts back here at the engine and using a perpendicular flange here in the front. This is a fairly complicated design, and I would really like to have a 3D model of this engine, but fortunately, I think we can get one. A little while ago, RevoPoint asked me if I wanted to check out their Metro Y scanner, and I think this thing will be appropriately crazy for this project. However, just like with this gas turbine, I have no idea what I'm doing with this 3D scanner, so again, we're gonna learn together. This thing did come with a pretty bewildering array of cables, tables, handles, and doodads, but it's definitely gonna be worthwhile to have an actual model of this thing to work off of. I don't think we'll be modeling these insane exhaust straight pipes, but we'll definitely be running the engine with them. Step one to creating the model is gonna be figuring out how to use this thing. It looks quite complicated, but it's actually pretty simple. There are multiple different laser projectors here, a cross line, straight line, and single line. They're gonna project laser patterns on whatever it is you're trying to make a model out of. Those laser patterns will take the contoured shape of the model as they're being shown on it, and then two special cameras in very specific positions will watch those lasers and create the model from what they see. Now, beyond the basic principles, I have no idea how to use this thing, so we're going to learn together, and part of that's going to include this automatic turntable. I set up the Metro Y Pro, and this also included metal tripod. This thing's pretty nice. And then after installing the Revo Metro software and getting everything connected, you can see we've got some cool patterns on my hand here. I've also dimmed the lights so that it can see better because it's really bright with the studio lights on. They give us this little bust to scan, but that's boring, so I went ahead and 3D printed a benchy. With the scan started, leaving everything on automatic, I'm going to go ahead and spin the turntable. And then after fusing the model using the recommended settings, you can see it's pretty good, but the 3D scanner wasn't able to see parts that were shadowed by other parts of the benchy. So what I'm gonna do now is start a second scan, go handheld, and get all those places that we missed with the first scan. Now, so far, this has all been done with the cross-line scanning, which you can kind of see blinking here. It's not blinking in real life, that's a refresh issue. But I can change that to parallel line scanning, which allows us to get more depth and features, or I could change it again to single line scanning, which allows us to get even more depth and features. Once I'm done with that, I'm gonna take each one of these models that I've created, run them through the fusion process, which basically puts all the points together. Then I'm going to use the included tools to cut out all the stuff I don't want, which is the base and all the stuff around it. There are automatic isolation and duplicate removal tools. I'll just let that all happen automatically as well. I'm not going to smooth anything because I want to see how this thing looks right off the scanner. And then finally, when we're done with all that, we can mesh each one of the images, and then we can merge those images together using the automatic feature detection system, which looks like it has worked perfectly. After merging, filling holes, and smoothing it, we'll go ahead and export the STL, bring that into Bamboo Studio, fix all the non-manifold errors, and go ahead and print it back out again. And by the way, off screen, I also went ahead and scanned their sample model, and it turned out to be much, much easier. Obviously, I don't know anything about 3D scanning, and something like this is pretty difficult to scan with all its little inside areas and things being shadowed by other things. Another thing that's hard to scan are shiny objects, and I think this is going to be about the worst torture test we can do for this scanner, and for my skills, which right now are 0. Now, speaking of things I don't know, while that's printing, let's talk about how this thing actually runs. Of course, all that starts by putting some fuel in a fuel tank. This is the fuel tank we're going to be using. It is an aviation tank, and it's got this thing called a clunk in it. That's designed to always be down no matter which way the airplane is oriented. Of course, hopefully this thing won't be oriented any way but up, given that we're going to be running it on a bench. Being a real gas turbine engine, it runs on real jet fuel. Fortunately, jet fuel is pretty much just kerosene, so we can also run it on regular old kerosene. I got this from Walmart. The only special thing is we need to supplement it with some of this King Tech turbine oil, and that's going to work the same as two-stroke oil in a two-stroke engine, keeping all the bearings nice and lubricated. Pump Pumping that fuel and oil is going to be this adorable little brushless fuel pump. That's going to be controlled through these wires, and the whole thing is going to be run through this little ECU, which we'll be able to monitor using this screen. Now, in a few minutes when we go to actually light this candle, it is going to be very loud and pretty crazy, so let me tell you what's going to happen. Basically, through the transmitter or possibly through the screen, I'm going to tell the ECU to start the engine. It's going to start pumping fuel through this fuel pump, which will get pushed into this inlet. Well, at the same time, this motor will start spinning this impeller in here, which you can see I can spin by hand. That's going to start compressing air inside the engine, where fuel will then get added, as well as spark, which is going to ignite that mixture. That mixture is going to burn, passing through a turbine, which is another set of blades, kind of like what you saw on the front. That turbine's going to get spinning, which is connected to these blades, which will spin even faster, compress the air and fuel even more, etc., etc. Meanwhile, on this end, the hot gases will be exiting, spinning this other turbine, which will begin to spin this output through the reduction gearbox. I don't want to do that without a load on it because it'll probably over rev, so I have this propeller we're going to put on here. This prop is technically too small, but I'm going to keep an eye on the RPM and make sure we don't bring the engine up to a speed that over revs it. And of course, once we make sure everything works and of course have some fun listening to this thing scream, we're going to figure out how to put it in an RC car. Now, while we were looking at that, our second generation Benchy finished printing, and wow, this thing looks really good. It's kind of hard to see in the white, but comparing it to the original, there isn't a lot of difference. There's definitely a bit of detail lost here underneath the roof. It's a bit sharper on the original one, and there are some artifacts on this side from where I didn't quite get it scanned in completely. But overall, for me being a complete idiot and this being my very first scan, I think that came out pretty well. And that result means I'm now completely qualified to scan this very complex, probably torture test of an engine, so let's get started. I don't know if I mentioned it before, but the scanner uses a series of these retroreflective marker dots to track where it is in space. Retroreflective basically just means it reflects light back at you no matter what angle you're shining the light toward it at. This is the same technology used on road signs and road markers. Of course, this turntable is a little bit small for our gas turbine engine, so I stuck a bunch of markers on this board, which is just a little bit bigger. But to have the best chance of success scanning this, I also created one more thing, and that's these little 3D printed 3D marker blocks. That's going to allow the scanner to still see markers at a low angle, and hopefully we can get as much detail on this engine as possible. I'm going to do this with the lights off because the scanners don't really need much external light, and this will let the cameras see the lasers even better. Let me work on this for a few minutes. Now that I've got models created from several different angles, I'm going to do the exact same thing I did with the Benchy. Starting with this one, I'm going to fuse it, get rid of all the extraneous detail. I'm going to do a bit of smoothing on this, and we're going to mesh it. And then after doing the same thing to all the other models I created, we're going to go ahead and merge these together. Unfortunately, the automatic merge isn't working because the top and bottom detail on this engine are very similar. So we're going to do it by hand. Basically, all we need to do is take any two images, find 3 points that are similar on the images, and then it will do the alignment for me. I'm going to do that to all the images, and then we end up with this model, which is pretty good, though not perfect, as there's a lot of reflectivity on the original engine, and it really did struggle with that. That's not the scanner's fault. That's just the way it works with this kind of system, and it did admirably well for what we had to work with. Now, unfortunately, the orientation on this model is going to be something completely random, so we can't bring it into Fusion just yet. Instead, I'm going to bring it into this program called Zeiss Inspect. It's a free program, and it allows us to do something called a 3-2-1 alignment. This basically lets you constrain each plane in turn. I'm not going to pretend like I know how to use it, but I am going to bumble through it, and then we can import it into Fusion, where I've already created my first attempt at the base for this. And as you can see, it fits pretty well. There's a little bit of clocking issue between the back mount and the front mount, and my measurement must have been off because you can see that the rear of the engine doesn't quite line up with the rear mounts. And as you can see from this first prototype that I printed before I scanned the model, it's absolutely correct. This band is just a little bit behind these holes, so let me fix this, change a few other things, and now hopefully this second prototype will fit perfectly. Just pop the engine in here, and yes, those holes line up really, really well now. I also added some reinforcement here in the front, so when it gets pulled forward, it doesn't rip these tabs off, and I added some screw holes for mounting. But of course, this thing's printed in PLA, and that's not going to work because this exhaust gets very, very hot. And that's where this crazy stuff comes in. This is Bambu Lab PPS-CF, and this wicked 3D printing filament has some crazy properties. PPS stands for polyphenol sulfide, and CF stands for carbon fiber. This is a semi-crystalline material, which means it's very strong, but very brittle, and it prints using some really wild settings. Materials like this PLA that we made the Benchy out of printed around 200 degrees Celsius. This stuff prints at about 330 degrees Celsius. It also requires a heated chamber and a very high temperature bed, which means we can't print this on a normal printer, and that's where the H2C comes in. This beast of a 3D printer can print up to 350 degrees Celsius, has a 65 degree C chamber temperature, and 120 C heated bed. And Bambu Lab was nice enough to send this along for me to show you for this project. Now, there are two other models in this range with the same basic specifications, the H2S and the H2D, but what neither one of them can do is this mechanical porn. What you're seeing here is the nozzle change system, and it's what sets the H2C apart from pretty much everything else. Without getting into too much detail, this allows you to have different nozzles for different materials without having to purge a bunch of filament, which allows you to do multicolor smaller and multi-material with a lot less waste. Of course, we're here to see if we can 3D print a mount for this engine, and we're going to do it with this PPS-CF, but we've got to prepare it first. This needs to be dried, and just like everything else about this material, drying isn't normal. Unlike a normal filament dryer, we're going to have to put this thing into a convection oven because it needs to be dried at between 100 and 140 degrees Celsius. With that dry, we need to prepare the H2C because its brittle nature means we need to fix the filament path to have fewer bends in it. We'll do that by pulling the guide tube out of its normal position, feeding it through the back of the printer, taking our now dry filament that's been in the oven for the last 8 hours, feeding it directly into the printer, and then we can get this print going. I'm printing this on the engineering plate with Vision Miner nano adhesive, and as you can see, it's laying down very nicely with just the default settings. This print's going to take about 12 hours because it prints pretty slowly, but when it's done, we end up with this masterpiece. This stuff is dense, heavy, and feels really weird. Unlike regular plastic that sounds like this when you hit it, PPS-CF sounds like this. It almost sounds like metal or ceramic. And by the way, ignore these issues with the top layer here. I actually put too little infill in. That's my fault, not the fault of the material. The same thing happened here. It's just harder to see. But this mount still isn't ready to go. We need to do something called annealing, and that's going to create more of a crystalline structure to give this better heat resistance and strength. To do that, we're just going to put it back in the oven, crank it up to 120 degrees C, and let it sit in there for 6 hours. While dinner's baking, let's talk about how we're going to hook this thing up to our X Monster. I don't yet know how we're going to mount it, but I do know we're going to need a gear, and all the gears that I could find that are big enough had an 8mm bore, so we're going to need to bore this out to the 10mm shaft size on the engine. And I say that optimistically because gears are pretty tough, and I'm not sure my Carvera is going to be able to do it, but let's find out. First thing we need to do is make a jig that'll hold it in place. I'm just going to use this piece of plastic. The first thing we'll do is drill a hole that'll hold the outside bore. We can then perfectly position it in that bore, and then hopefully we can slowly mill out the center to 10mm. While that's machining, we've got one more thing we need to do to this now annealed mount, and that's add a little bit more heat protection. Because while this PPS-CF is very heat resistant, the exhaust is going to be right next to the front here, and I don't think it's that heat resistant. To take care of that, we're going to be using real gold. Heat is transferred 3 different ways: through convection, conduction, and radiation. Radiation is the one we're worried about here, and metallic gold is one of the best reflectors of radiant heat you can get. If you're going to do something like this, though, you need to make sure the stuff is actual gold. There's a lot of gold-colored heat reflective tape out there, and the color itself doesn't do you any good. It is the actual gold itself that reflects the heat, so you need real gold. I'm using this DEI reflected gold. It's very well known and has a really good reputation. And now with that done and looking very fancy, we can finally get our engine mounted up. All right, guys, everything is strapped down that can be strapped down. The fuel pump is primed. Let's light this candle. All right, here it goes. Might take a couple tries just because we don't have all the fuel all the way into the engine yet, but it might light off on the first try. We'll see. Spinning up. I hear a little something going on. Sounds like there's fire in there. Maybe? Oh yeah, I think it's starting. Here we go. There she is, guys. She's running. Give her a little of this throttle here. All right, yes, it works. Absolutely awesome. Well, guys, that was absolutely incredible, and you just helped me check off one of my bucket list items, but now let's see if we can get this in an RC car. To do that, first we need to strip down this X Monster and get all the stuff we're not going to be using out of the way. Now, after removing about 20 screws, this all should come out as one big lump. I've never done this before, but yeah, it does. With all that removed, we've got a pretty big area to work with, but I want to 3D model it so we can bring it into CAD. Because this is too large to put on that plate or even on my board that I created, we're going to have to add tracking dots directly to it. And this is really just a matter of adding a bunch of these to flat surfaces all over the area we're going to scan. The system can automatically remove these in post-processing. So let me get this tedious job done. And now after adding an entire sheet of those dots, which will hopefully be enough, let's get to scanning. This time we're going to going to use the scanner's wireless capability by connecting it to this included battery handle instead of connecting it directly to the computer. That should make scanning a bit more convenient. And now after firing up the software and killing the lights, let's get this thing scanned. After finishing that scan, cleaning up the model, bringing it in and aligning the axes, then bringing it into Fusion 360 and putting it under the scan of the engine, we can see the engine will physically fit and we could start making mounts from here. But there's another problem. The problem isn't that the Carvera made a beautiful, smooth 9.9mm hole. I checked the CAD and I actually had stock to leave turned on, so we could easily fix that. No, the problem is that this gear on this output means this output would have to be standing still some of the time when the engine's running. And even though this is a free spinning turbine, meaning that the input for the drive is not directly connected to the output on the engine, that drive input turbine is designed to be spinning all the time. And I'm really scared that even holding it still at idle, we're going to end up burning up that turbine. I asked King Tech about this and they were unhelpful to say the least. And I don't blame them because of what I'm doing with this thing. And while some full-size turbines can be held still, I don't want to take any chances, but I've got a different idea. I was unable to find any kind of appropriate clutch to put on here. They were all either way too small or way too big. But what we might be able to do is connect an electric motor to this, which we can turn into an alternator by driving it, run that through a VESC that has regeneration capability, and use that to keep the batteries topped off and drive the truck. You might be surprised to know that a very similar system is used in nearly every full-size locomotive today, though instead of a gas turbine, the vast majority of them use giant diesel engines, but gas turbine generators are not unheard of. To put these together, I want to create a custom coupler. We have 10mm on the output and a little under 6mm on the input, and this is where the H2C is going to come in really handy. Because it uses wireless, inductively heated, automatically changing nozzles, we can have something like PETG in one and TPU in the other. And that means in CAD, I can create a coupler that's solid on both ends, but has a nice soft core for a little bit of compliance. This gives us another opportunity to watch the mechanical dance of this machine switching nozzles, and let's get this thing printed out. While this is printing, I'm going to make a mount for this motor that's at the same height as the mount for the engine. That's going to be pretty simple, so I'll just do it off camera. And now while that's printing, let's talk about this VESC. On the surface, this just looks like a standard ESC. We've got power that comes in, power that goes out, and a way to control it, but it's so much more than that. As the name implies, this is running the VESC software, and that creates the opportunity for a ton of customization. If we go ahead and fire up that software, you can see there are a bewildering amount of options in here, and using these options, you can make the ESC do pretty much whatever you want. Most ESCs we buy for surface bashing have a few options, but it's nothing like what you get on a VESC. And to be honest with you, I have no idea what I'm doing inside this software. What we need to do, though, is create a system to where it actually does regenerative braking so that the motor can act as an alternator being rectified through the ESC and actually charge our battery. I've asked ChatGPT and it's told me a few different settings to change in here. Hopefully these are correct, but I'm leaving pretty much everything else alone and at its defaults. Again, hopefully that's correct. The motor we're going to be testing with is 380 kV. Based on my calculations, that's probably a little bit high for what we need to do. But the problem is once you go down to lower kV, you end up with much larger motors. And for testing, I think this will work. What isn't going to work for testing are these normal size batteries. So we're going to go with this giant 100 amp hour 4-cell lithium iron phosphate unit. This thing can be charged at a maximum of 100 amps, which means we're probably not going to be overloading it while we're doing testing when I don't know what I'm doing. Speaking of not knowing what I'm doing, while this print came out really cool with a nice flexible center and rigid couplings on both sides, I don't think I'm going to use this. This whole setup's going to be spinning at a few thousand RPM, and if I mess something up, it might damage the engine, and I really don't want to do that. So I think we're going to go with one of these ready-made ones. This one has a fairly rigid piece of what I'm guessing is polyurethane in the middle, and this one is cut into a spring in the middle, which gives it a bit more compliance. And even though this mount, which is printed in glass fiber ABS, again, a very nice print, should kit the motor exactly in line with the engine, I'm a human being and I'm probably going to get it a little bit off, so this should help with compliance. Another thing I don't know is if I've got this VESC programmed properly, and I want to make sure we don't over rev the output on that engine. So you see I've got a little bit of reflective tape here, and I went ahead and picked up this laser tachometer, and the laser will shine on it, creating a bright spot every time it rotates, and there's a sensor in here that can see that. That'll give us an accurate RPM reading on this screen, so I know I'm not over revving the output on the turbine. And with that, I think we have everything we need. So let me get all this stuff set up and let's go see if we can make some electricity. All right, guys, we've got a lot of moving parts here. We've got the motor mounted. We've got everything aligned as best as I could get it. It seems to run very smoothly. We've got the turbine here. We've got all the electronics over there, the VESC running down to the battery. Let's see what this can do. Initial spin up. Fuel pump going. I hear flame. Starting up. Can smell the smoke. And I think she's starting to go. Should see that motor starting to spin soon. Okay, I've got bad news, good news, and great news. We'll start with the good news. This PPS-CF 3D printed mount held up absolutely perfectly. I'm sure the gold reflective tape did help, but it's pretty amazing we can use a 3D printed part right next to something that's several hundred degrees with no issues. Overall, this worked out perfectly. That just leaves the bad news and the great news. The bad news is I don't think this particular engine's going to do what we need it to. I'm pretty sure direct drive with this output being held still would burn up that turbine. I wasn't able to find a clutch for it, and in spite of my best efforts, I couldn't get this motor to work properly. Results through this VESC were really inconsistent. Now that might just be my programming issue, as I don't really know what I'm doing with these things, but the load kept jumping up and down, and that's really not good for something like this. I did end up just switching to some simple resistors just to put a load on the motor, and that did work, but it's not controlled enough to actually do anything worthwhile. Now that's just how these things go sometimes, but there's two bits of great news. First, we got to mess with this amazing engine, and second, we're not done by a long shot. I've got two more things coming that are going to make for amazing redemption. You are not going to want to miss those videos, and we are going to make this work. All right, guys, so consolation prize run. I definitely want to see this thing go one more time. So we've got the prop back on, everything's set back up like we had it originally. Let's fire it up again. All right, here it goes. We got some smoke.